All right, yeah, go ahead and pass all the quizzes in over to the door side to your left. Quiz 3, look at this. And the attendance is coming around.
Do you have a quiz, Andy?
I turned it in on Monday.
Okay.
Sorry.
Sorry.
Any more? All right. All right, so on the Teams meeting we were doing for all and there exists. So I'll review that a little bit. Make sure everybody up to speed on it. It's chapter 3.1. So for these questions, like we'll just do them by example today. You have a given set that they tell you what the set is, the collection of input values that you might have to look at. And then they say decide true or false. And then there's these two new symbols. The upside down A is the one that's for all. So this part of it here would be, in case you didn't get this yesterday, was you read it out loud for all Q in the set B, like that. So what it means is that for checking that it's true, you have to check all the input values that are in the given set. So I have to check -1, -half, and 0 to see if it's true. So I'll just check them all. So check all all the set. So Q equals -1. I'll check that one. Q equals -1/2. And Q equals 0. So when you check it, you don't have to check the for all part. That's what the list is. So the part after the comma. Is what you have to check. So I'll plug in Q equals -1 after the comma, and I get -1 less than 0, and -1 squared is 1, 1 greater than 0. So that's two true statements, true and true. So I get true, and then Q equals -1/2. -1/2 is less than 0, so that'll be true. And -1/2 squared gives me +1/4. So true, true. But I think the third one messes it up because I use strictly less than without the less than or equal to on this one. So I get 0 less than 0, but that's false. So I already know the and is not going to work, no matter what the next one is. It's actually false too, like it's 0 greater than 0. But that's also false. So I get false and false, definitely false. when we check it. 0 less than 0, and 0 greater than 0. Yeah, so good. So, as soon as you get an example that gives you, or one of the input variables in the list that gives you false, that means you know the whole thing is false. So, therefore, the whole statement is false. That's the answer. And then the one bad number that made it false, there could be more than one too. All it takes is one though. So any number that makes it false, we call that a counterexample. At least one making that turns out that the part after the comment is false makes the whole thing false. You only need one of these. Or more. More would work too, but what I mean is you only need one, right? To make the whole thing false. I'll use the verb of it there to falsify. Or you could say to prove it false. Right there. We're going to use the word prove more often now. Because it's like we were kind of doing that already. You just had to check whether it was true or false. You know, I would say, here's a statement, plug in a 2 or a -1 or something, decide if it's true or false. So I just said decide. But that was kind of proving that it was false. You just had to just check it, see if it was. Now, since there's a little bit more work to do, you call it proving it. You know, you have to say sort of at least one extra step besides just checking, and then they start saying proof. But one step is still proof. It's just that you don't really call it proof until you make 2 steps. Here you check them until you find a counterexample, and then the counterexample proves it false. It's almost just one step still, but. We should do a there exists one too. To get back into the mode of doing these. So there's an example for there exists. Let me do same B. And I'll say prove this statement true or false. There exists an X element of B such that, and then a new statement for it. Let's see, go with X is less than 0. Simple. That'll probably be easy, but that's okay. 3x plus 1 is greater than -2. Okay. Maybe make it greater than or equal. Okay. So, just for an example. So, the proof of this statement to be true would be to find just one example. All you have to do is find one example that makes it work. So let me put that as a statement. I don't know which it is yet, and it might be pretty easy, but to prove it true, we only need to find one example from B that makes, so one example X, some X from B that makes the part after the such that true. So, when I get one of these, I'm tempted to just do it in my head and try and figure it out first if I can just spot one that's making it true. So, I've got 0, -1, and -1/2. Alright, it has to, it's an and, so it has to be the -1 or the -1/2 working. That's hard. So I put the -1 in, I'll get -3 + 1. That'll give me a -2, and that actually works. So I can go with that right away. There may be more than one that works. I'll mention all of them, but here's one that works. So the answer could be this solution. X = -1. Shows the whole statement true. Since the part after the such that is -1 less than 0, and 3 times -1 + 1 greater than or equal to -2, and that's -2 greater than or equal to -2. So that's true, and that's true. So that's equal to true, or 2. True. As a note, you could try 0 and it wouldn't work. You could try -1/2, and I bet that one would work because you just have to do the fraction there. It's less than 0, and -3/2 + 1 gives you back to just -1/2, but that's greater than or equal to -2 as well. X = 0, and it doesn't work, but X = -1/2 is another solution. Showing true. So definitely a true statement because there's at least one example that makes it true. In case this time there's actually a couple examples that make it true, but all you need is one. So to sum up, to show a for all statement true, we have to check all the input set. After the comma. So the after comma statement must be true. For each of them. To show that a for all statement is false, all you need is for one to become false. We just need one counterexample. And then for the there exists, it flip-flops. To show a there exists statement. True. For that, you just need one example. So just one example that makes the part after the such that true. But to show that there exists false, then you have to check them all and show that they're all false. Check all the set again. You have to get false all the way along. So you get false for all of the whole set on the statement after the such that. Now there it is in words one more time. From the examples. The examples are pretty good too, but then you can, once you see some examples, you can sum it up like that. That covers it pretty well. So the next thing is to apply the not operator to these kind of statements with the for all and there exists. Basically to see how to negate them. And the punchline is that when you negate them, they just flip-flop, because you can tell that just from the words, they kind of are opposites of each other. You either have to check all of them to show that for all is true, or check all of them to show that there exists is false. And you only need one example for all to be false, and you only need one example for there exists to be true. So when you negate them, they turn into each other. So that's the next kind of question you have to be able to answer is simplify the negation, but with the for all and there existent. I'll show you the rules, but the examples are better. Good. The examples will make it easier to understand. For the rules, it's a real simple thing to write down, but then I have to try to add some description so you know what the pieces mean. Negating for all and there exists. So, two rules. Number one, if you do a not, and inside of the not, there's a for all. For all x element of s, comma. And then there's something else. So the something else could be a whole bunch of things. Could be a whole complicated statement. Let's call it, just call it Q, I guess. So, just so you know what that is. It can be any compound statement. simple statement, a compound statement. It can be any statement at all. After the comma. That's the part that we've been checking when we do it. Check for all there it is. So S is a given set here. Just in case. That's clear from the context. Now we've got more capital letters going around because we have capital letters that stand for a given set too. But from the context, those will always have things like this little epsilon symbol where it's element of or in X in S in front of it. Okay, so what this is, the rule says that this is equivalent to putting the not into it, and when you put the not in, it flips it to there exists X element of S, such that. So the for all turns into there exists. X element of S is copied exactly. The comma turns into such that. You know, like trace these down. That goes to that. All of that stays the same, but the comma turns into such that. And then the not goes on the Q. So you have to negate the rest. Then the other rule just runs it backwards. But to see it, you should write putting the not on there exists X element of S such that some statement now. This can be any statement at all, so I'll just put a P here. Such the P. So same thing applies. P can be any statement at all. And when you apply the negation to a there exists, it turns the there exists into a for all. Keeps the X element of S, turns the such that into a comma, and P into not P. So that comma there is kind of important. It really is a separator from being making it clear whether X element of S is the quantified part of the statement or part of the P. You know, although I'll probably just put it in for you. Forget it if you forget the comma at first, anyways. But kind of need it sometimes to make it not ambiguous. So that's the rules, but you got to see it in operation, see it happening. It's too short and simple over there. Got to make it see what actually happens on these. But what the punchline is just making you do the same problems that you had to do before over again, with just this little bit out front. But everything else, same again. So, for an example, you could say, the question could be asked like this: simplify the following negation, and by simplify, I could say, make sure you don't see any not symbols. Just like before, simplify it so there's no more not symbols anywhere. Okay, so here it is, not, and then for all y element of r. Oh, I'll use some of these classic names for number systems. So for that one, we'll just let R be the real numbers. Is a double bar R. So we use some of those. First time I use them, I'll remind you what they mean. Okay, so for all y element of R, comma, Let's go with a y is greater than or equal to 1 implies y squared greater than or equal to 1 and 3y greater than or equal to 30. And we need a big parenthesis for that not, and I also better put parentheses around here. Yeah. Okay. So this time on this kind of question, I put the not symbol on there for you. Another way I could say it would be just negate the following statement, and I could just write the inside of it. So you could say the question I'll do the next one that way. I'll do one where it says, instead of simplify the following negation, I'll say negate the following statement and simplify. Same thing though. This time I wrote the not symbol for you. So now it's ready to go. Okay, so the answer would be, I'll do it in some steps. First thing you do, you put the not symbol into the big parentheses and you use the rule that for all turns into there exists. And the comma turns into such that. The y element of R stays the same. Keep that. Then you're supposed to put the not on Q. Okay, so that is the tricky part about writing down those rules, is that the first thing establishes the pattern. So Q in there is any compound statement. That means that this thing is all Q. Everything after the comma is Q. So if I'm using the rule, I need to put a not on all of that. So I'll show what that looks like. Such that not, and then everything else. Y greater than or equal to 1 implies y squared greater than or equal to 1 and 3y greater than or equal to 3. Yeah. So far that's equivalent to that. That's just like, that's doing the rule. And now, if I'm supposed to keep simplifying, I have to do the not on the rest of it, which is now it's back to a problem that we've done before. Now it's doing not on an implication. So, and you look back at the old rule, and it's got P's and Q's as well. But what it says in words is to keep the first half, change the implies to and negate the second half. Yeah, question?
What is the difference between the comma and the ST?
Well, it's easier to describe the ST since it says such that. And that it means when you start out by saying there exists, you're saying there's some example, and then you have to describe what's true about that example. So there's some example such that it does this. If you just left it as a comma, you would say like there's some example, comma. Probably it would make sense to most people, even if you just left comma at both places. But yeah, I guess it's really forcing it into an English language sentence, to keep such that. That's like English language. Comma is what you would put for all y. You could change the comma to say for all y element of R. It is true that, but that's too long. So we just say comma. For all y element of R, y greater than or equal to 1 implies, yeah.
So would you say if you're using a comma, you're quoting the entire set, whereas if you're using such that, you're only quoting a piece of it?
Yeah, the such that just traditionally goes with there exists. If you say for all y element of R such that, it sounds like you're starting to describe the premise. You know, like you're trying to say not just for all y element of R, you're trying to say for all y element of R such that. Then you would have to go like for all y element of, put a different bracket around there and say R such that, and then describe something special about R. That wouldn't work out very well. You could say, it's a mess, but you could specify something about the R, like just put it in words, real numbers larger than 2. So that looks like for all y element of real numbers such that they're greater than 2. So just to keep it from sounding like that, I won't use the word such that on the for all. Makes it clear. Yeah, but I'm not done yet with the answer here. I need to finish simplifying it, right? So one thing to be careful of is if I've already done part of it, like I did the not on the for all, I don't want to accidentally do it twice by just getting in the groove and flipping it again. I've already done that. I'm just copying it here. I just need to finish doing the not on everything else. Okay, so the not on everything else. If I have an implication, what I need to do is change that to an and. Then I keep the first half of this. So I was writing a little note about it since it's been a while. So I keep y greater than or equal to 1. Change the implication to an and I'll show one more step. Now maybe I'll just write it because I have space. I want to knot all of this. So all of this is going to be knotted, and I'll use De Morgan's laws on that part. Okay, so that means it'll look like y squared less than 1. That's not of that. But the and turns into an or. And this will be 3y less than 3. So that's the final answer there. There's no more not symbols showing. I just put some little notes to see where it was coming from. When you knot an implication, keep the first half. Error turns into and, not the second half, but now it's De Morgan's. So you can think about that's just the question there, just negate it and simplify it. But the reason for being able to do that is that it can be really handy to think about one or the other of the two. Like instead of proving that the original statement is true, I could negate it and then check that that's false, or vice versa. You could, instead of checking that the negation is false, I can prove the original statement is true. So the motivation, this might be useful. To show the original statement, I mean without the not on it, like the for all y element of R, comma, y greater than or equal to 1 implies y squared greater than or equal to 1 and 3y greater than or equal to 3, that one. We might That could be handy. This time, I don't know, I think the first one is true, right? Because it looks like anytime you take a real number, what about negatives though? Let's see. Yeah, so it looks like this is actually good. And so instead of showing the original statement true, I bet you can show the original statement as false this time. And to do that, the there exists statement like clarifies what exactly would be a counterexample. So here, to show the for all statement is false, that there exists the negation of it which looks like there exists describes exactly what a counterexample would look like. You know, to show that the for all statement is false, you want a counterexample. So you want a y value that makes the whole thing false. So you can do that. You can just look for a y value that makes the part after the comma false. But once you negate it, the there exists shows you exactly what that y value should look like. It should be a y value that's bigger than 1 or equal, and its square is strictly less than 1, or it's 3 times it is less than 3. Okay, so I don't know, which one is it? Is it true or false? As in, is there a counterexample?
There isn't.
Oh yeah, maybe not.
You have a negative.
Since you're bigger than 1, you can't use a negative, so you can't get either of those things to be false. So they're always going to both be true. Yeah.
So would you call that a
Yep.
tautology?
Oh well, what we do is say that this is a true statement. The for all statement is true. The there exists statement would turn out to be false because it's the negation of that. So let me just conclude there. But this time, the for all statement is true. Now, we haven't written down a proof of it yet, but that's something that we'll work on next. The way to actually prove this one won't be by listing all of the possibilities, right? Because it says for y element of the real numbers, and that's an infinite list. Instead, we'll have to break it down into some things that we can substitute in, make some assumptions about the y, and then substitute them in and check that it shows that true does, whenever the first part is true, the second part has to be true too. That's for the next section. For now, just negating it, and the stuff I wrote on the sides outside of the box is motivation for the future, what we're going to use this for. It might be useful to work on proving it one way or the other. We should do one more negation where it starts out with a there exists. Any other quick question? So here's one with just a simplify again. So another example would be, this time I'll write it this way. I'll say negate and simplify. Okay, so this time I'll write the statement. There exists y element of the real numbers such that for all x element of the real numbers, comma, x plus y less than 2 implies x, that's a messy x times y as less than 10. Period. Okay, so, yep, this should let you know you can mix them up. There can be there exists and for all in the same thing. But now just make it clear how you can use the rule to do this. So we're gonna negate it and simplify. So we're just gonna apply not to the whole thing. So we're going to apply not to this thing. So just take a big not and apply it to this. All right. So that means I'm applying a not to a there exists statement. So it's got there exists x element of something such that, and then a lot more. So that means that everything after the such that, like all of this stuff, is going to be what I called P over there. Everything after the first such that in the rule. And I'm going to have to use the rule, use both rules on this one. So the answer looks like change the there exists to a for all. Change the such that to a comma. And then this is equivalent to I haven't really done anything. I'm just I'm negating it. Negating the whole statement. Okay. Oh, no, that'll simplify it after that. Now I just want to apply not to everything else. For all x element of r, comma, x plus y less than 2 implies, I haven't done anything yet, x, y less than 10 on this part. I'm just showing my work. Okay. It's tempting to just do these problems by just taking the not and going straight through and getting the answer in one blow. It's possible if you're really focusing, but the problem is it's easy to forget where I'm at as I'm doing it. And I'm like, okay, did I already not this part or not? And, you know, if I'm trying to do it without showing any steps. So I'm breaking it down a little bit here. So this is going to be for all y element of r. I already did that part, so I'm just copying it. Now I'm going to do the not on everything else. So that means I'll use the first rule because I'm going to change the for all into a there exists. Now x element of r. And the comma into a such that. And then the not on everything else. X plus y less than 2 implies xy less than 10. And it'd be tempting to just go ahead and do it, but I'll show one more step because then you can see what I did each time. Now I'll apply the not to the rest of that, and it's a little bit more familiar. We've done the implications so many times. I'm going to keep the first half, change it to an and, negate the second half. So just copying, comma, there exists x element of r, such that. Now keep the x plus y less than 2. Change the implies to an and negate the rest. I don't need the De Morgan's laws this time, so there's only one piece. So xy greater than or equal to 10. That's the final answer there. So, put that in the box. Yeah, I have no idea whether that's true or false the way it's written. It looks probably true. Like the original one is true and the last one's false, right?
If y is 0, then x times y can never be greater than that.
Yeah, no matter what x you pick, right? So the last one is false. That means probably the first one is true, right? Because if what's in the box is false, then the original would have to be true. So the original was an implication, so it's much harder to parse. You have to think, okay, x plus y less than 2 implies x, y less than 10. The only thing that can't be there exists in the original one is there exists, so you only need one y that works. Oh wow. So, yeah. Letting y be 0 in the first one means you found a y such that no matter what x you add to it. Oh man. I didn't mean for it to be a problem that you figure out whether it's true or false. So I'll leave that to you guys. It's just to figure out how to negate it. Any question on the answer there to the negate and simplify? Make sense? All right, I'm gonna think about it for a minute longer, but
Just really quick,
Yeah.
would you, if you were to have to find like the solution, like true or false for the last,
okay.
would you solve those separately, like the for all and the?
Yeah, you read it from left to right. So, like, is this one?
So you would say like, let's pretend like this one's true and this one's false, right?
Yeah.
Or if one's true, I mean, if one's false, then the whole thing be false.
Yeah, to decide that what's in the box is false. All you need is one y that makes it everything else false.
Okay.
But
the
then
whole,
you start with then you look at what makes everything else false. That means it has to be false for every x because it says there exists x, making it true.
gotcha. Okay.
Yeah,
Awesome. Thank you.
you might need to write that down and work it out a little bit at a time. Yeah.